Okay, so I suggest we start. First of all, are there any questions or comments? So some of you wrote to me concerning the Moodle platform. Yeah, sorry, it took me a little while to figure out how it works. But now it's okay. In fact, we even checked before on someone's computer, and you have to look under the French name, Théorie de l'information quantique, and there you have everything. Okay, so the lecture notes, the tutorials, even some of the corrections of the tutorials. So concerning the tutorials, are there some also remarks or anything? How did it go last time? So yeah, I have to say the tutorial number 1 is supposed to be a very easy one. Okay, so if you found it almost trivial, then don't worry, it will become a bit more tricky later. If you found it not so trivial, okay, maybe make sure you really understand it. Okay, no further remarks. Also, I have to say, last time I was very pleased because there were many questions. So, yeah, I encourage you to continue like this. I think it's really good. Okay, so let's start. So last time we did a quick recap on quantum mechanics, basically, and then we started discussing qubits, so our units of quantum information. And so we said a qubit is a state that is spanned by two basis states that we call 0 and 1, and then the most general qubit state is a complex superposition of these two, okay? And one always has this normalization condition, which is this, okay? And so then we started discussing measurements that one can do on these states, right? So for instance, we said, okay, so we can do a measurement that is given by these two eigenvectors, okay? And then we describe, for instance, what is the measurement statistics that you are going to see if your qubit state was prepared like this. And so then we said that the probability to see the result +1, so the +1 result would be associated to this eigenstate here, right? So that is going to be, you will compute it like this, right? So this is the Born rule for computing probabilities of quantum measurements, and that is going to be an alpha squared. Okay, and if you wanted the same thing with the -1, okay, then you have to do this. And then you see it's beautiful, these things sum to 1 as probabilities should, and that is, again, because we normalize things properly. So then we also discussed, states in terms of knowledge, okay? So, because these are what we call pure states. So pure states, they are states of complete knowledge. This is where you know everything that there is to know about the system, right? So according to quantum mechanics, you cannot, with this knowledge here, you can predict whatever there is to be predicted on measurement statistics. You cannot do more than this. And you see that if you pick a state here, which is not an eigenstate of this measurement, okay, so that means if both alpha and beta are non-zero, well then you see that you can only say something about the statistics of the outputs, but if I give you one instance of this experiment where I prepare this state and you do this measurement, the best you can do is to guess what outcome you will have, and this is this probability distribution, right? You cannot do more. And so, again, this is very important, right? This means that in quantum mechanics, even though you know everything about the state of the system, you can still not predict always what's going to happen, right? So, And so if you think of this in terms of knowledge, in terms of information, you see already that things are going to be very different than with classical information, right? Because with classical information, if you know everything there is to know about the system, well, then you know everything that's going to happen, right? Like in classical mechanics, for instance. All right. So then we can now look at other things. We can, for instance, look at measurements in different bases. Okay. So let me construct another basis. Yes, sorry. Maybe one thing I should say more is that so this is a special basis which we call the computational basis, and so this is a projective measurement, and for a projective measurement I can write an observable. I didn't write it last time, so if I write the observable corresponding to this measurement, okay, I'm going to write it mz. So I use this spectral decomposition, right, that we have seen. So I write my eigenvalue plus 1, then I write the projector on the corresponding eigenstate, and then I write, okay, let me do it really pedantically. So here you really see the spectral decomposition, right? Here I have the second eigenvalue with the projector on the second eigenstate. So that is a 2x2 matrix, right? This is my observable. And this is nothing but the sigma z. So this is the third Pauli matrix, okay? Right, and so in the exercises there were lots of things about this. Right, so when you want to calculate with these things, right, the typical idea is to represent this as a column vector, 1, 0, and this 0, 1, okay, and then you calculate things easily. And then, for instance, this matrix here looks like this, right? But, I mean, this vector thing, this is only a representation, okay? I mean, at the end of the day, we have objects here, and there is some sort of algebra as to how they behave. And I would say the most convenient way to represent this algebra is using these 2x2 matrices, or two complex component vectors. You could do in another way, right? But this is the easiest way. So when we talk about a measurement in the computational basis, well, then you should think of doing a Pauli Z measurement, okay? Or, okay, if you think in spins, right, if you like to call this spin up or in this spin down, then you do a measurement in the up-down basis. And so then obviously I can also do measurements in other bases. So another basis. So let me introduce two states. So these are, yeah, okay, maybe I should, let me do it step by step. So we will also often use the notation for what I call the plus state. So this is an equal superposition of 0 and 1, okay, with a factor 1 over root 2 for normalization. And, when I do that, I can also define a minus state that will just have the opposite phase here, okay? And, okay, it's immediate to check that they are orthogonal, right? So their overlap is 0. So they form a basis, right? And if they form a basis, I can do a measurement with them. So I do a measurement, and so these are my two eigenstates. And so, okay, again, the eigenvalues will be plus 1 and minus 1. Remember that this is just a convention, right? These are just labels. And so now I can also write the observable. Let me call it mx. And mx, well, if I use again the spectral decomposition, I can write it like this. Okay, so this means projector on the state plus, projector on the state minus. And you see, if I want to calculate this, it's better that I go back to to my preferred basis, right? So I can insert all of these things inside here. Needs a bit of algebra, and then I can get a matrix out of it. And here the matrix will look like this, okay? And so this is nothing but the sigma x Pauli matrix, all right? And you see that in principle, I can just imagine an infinite number of different measurement bases, because you see what I need to do is I pick one state here, one combination of alpha and beta. There will always be an orthogonal one, so I make a basis out of it, and then I do a measurement. Okay, so we said one fundamental difference between quantum information and classical information is that already at the most basic level, if I just look at a unit, right, while a unit of classical information has only two states, right, 0 and 1, a unit of quantum information has infinitely many states, right? And similarly, measurements, there is also an infinite number, right? I can make a measurement in an arbitrary basis. All right. So maybe let me just say one thing about an evolution, because at the moment I only described states and measurement, but we also talked about evolution. And so I want to look at an example, and this is a NOT gate. Okay, so this is the logical negation, right? So what a NOT gate does, think of it classically first. So if you had initially a 0, your NOT will map it to a 1, right? And a 1 will be mapped to a 0. Okay, so it's just a negation. And now, of course, I can also do that quantum mechanically, right? I can design an evolution that is going to do that, where instead of just having logical symbols, I put cats around it, right? So these will be my qubit states. And so I can define the unitary directly that is going to do this. So it's not a surprise that I actually call it mx again. Okay, but you see this mx is supposed to do what? Well, it's supposed to do the following thing. So imagine I apply this operator now to some state, right? If the state is 0, okay, so that component goes. I mean, I put the state from the right, okay? So this component goes. Here there is a 0 with a 0 that will just give me a factor 1, and then I have a 1, okay? So if I apply mx to 0, I get a 1. And similarly, if I apply a mx to 1, I get a 0. Okay? So this is indeed a quantum NOT gate, okay? At least in the computational basis, right? It's doing the right thing for me. And so you see this thing, well, in fact, this is again the sigma x matrix. Okay, but you see it's the same mathematical object, but it has a slightly different meaning, right? Here it's an evolution, it's a unitary matrix. Here it's the observable that corresponds to a measurement in the x basis, okay? All right. So let me just conclude this with two remarks. So two states can only be perfectly distinguished if they are orthogonal. Okay, so that was the idea that we discussed last time quite a bit, right? Is that if I do, for instance, this sigma z measurement, if I have the promise that the state is either a 0 or 1, right? If it's an eigenstate of my measurement, then I can perfectly find out which one it is. Okay, if I don't have this promise, if the state is not an eigenstate of my measurement, I will not find out for sure which one it is, and moreover the state is perturbed after the measurement, so it's not that I could start again. So you see, in particular, it means that for my qubit, right, I can have two states which are of complete knowledge, and still I cannot tell by any possible quantum measurement which one it is, right? That is an important thing. So maybe let's write this quickly. So there exist pure states that cannot be perfectly distinguished. Okay, and so now, in fact, so in fact, this is any pair of non-orthogonal states, right? So any pair of pure states that have a non-zero overlap, you cannot perfectly distinguish them. But okay, here we are talking about perfectly distinguishing the two states in a deterministic way. Okay, but you could add what happens if I'm just asking to do that probabilistically. So this brings us to an interesting example. So let's write it. So however, this is possible probabilistically. So we will probabilistically. Okay. So the point is that if I'm giving a pair of two states that are not orthogonal, so let's do an example. So here are my two states. Okay. I take the 0 state and the plus state. Okay, and obviously the overlap between the two, okay, this is 1/√2, so this is non-zero. Okay, so if I'm given, so if there is a source, right, someone prepares either the state 0 or plus, sends it to me, no matter what quantum measurement I do, I will never be able to tell for sure which one it is deterministically, okay? However, it's interesting because I can do it probabilistically. So that means that in some cases I will be able to tell for sure which one it is, but my measurement, if you want, will not always work. So in some cases I will have to say, I don't know. And in fact, that's interesting because this brings us to these general quantum measurements, right? I mean, so far we discussed projective measurements, but remember last time I introduced a slightly more general framework for quantum measurements, so-called POVMs. And so the measurement that is going to do this distinction task, it will be a generalized measurement. This is something that would not be possible with a projective measurement. So let's do this. So in fact here, this is possible by using some POVM, right, a generalized quantum measurement. And so here is the explicit POVM. So remember, how do I construct a POVM? Well, I have to give a collection of operators that are positive and that sum to identity. So here is going to be my first measurement operator. Okay, so it's, you see, it's this part is a projector, but there is a constant in front. Okay, I will specify later what that constant is. Here is my second element. In fact, let me just remove the subscript. It's anyway going to be the same constant. No, why is it not the same? Okay, let me leave it. Sorry, I have to think about this. Okay, so here I have specified my first two POVM elements, okay, my first two operators from my measurement. However, I guess you already see that they don't sum up to identity, right? So like this is not a measurement. But I can make them sum to identity by just adding the following thing. So I add identity minus E1 minus E2. Okay? So in a sense, I cheat, no? Because I just complement that thing. But, okay, so here comes a subtlety, right? Remember that, that all of these things have to be positive, right? Now, these two are obviously positive for any C1, C2, okay? Well, I mean, any C1, C2 that are non-negative. Now, what about this one? When is it positive? And in fact, this will imply conditions on these coefficients here, okay? But if I pick, sorry, I'm confused by this. I'll check it later. To me, this sounds weird, but. So if I pick my constants like this, okay, then the claim is that that thing is positive. I think you have it in the tutorial, so maybe you can check it. Now, okay, why is that an interesting POVM? Well, okay, so the idea is that, what can I say? So if I see the outcome 1, okay, so the outcome is the label here. So if I see the outcome 1, okay, what can I say about the incoming state? Well, you see, 1 is orthogonal to 0, right? So then I can say that if I see the result 1, well, then for sure it was not the state 0. But given that the state can only be this or that, well, if it's not that, then it has to be this. Okay? So then, so state is plus. Okay? And so similarly, if the outcome is 2, so if the outcome is 2, well, because here you have a projector on minus, which is orthogonal to plus, if you see that outcome, well, the state had to be 0, okay? So here the state is 0, okay? And so that's exactly my probabilistic distinction between my two non-orthogonal states, right? Because in case I see outcome 1, I know what the state was, it was plus. If I see 2, the state was 0, but, you know, obviously in some cases I have the outcome 3. Okay, so if I see outcome 3, then I don't know. So that is the, you know, where the probabilistic nature comes from, because somehow it's like, if you want, it's as if my measurement didn't always work. Okay, with some probability, I have to say that I don't know. And so, I mean, you see, right, that these things are, they are not projectors, strictly speaking, because of these constants. So this is really a generalized quantum measurement. Oh, actually, sorry, maybe one thing I can add here. So I could say, you see, what is interesting is maybe to also say how often I have to say I don't know. Right? Because if this would be 1 out of 10 to the 20, well, okay, then I don't really care, no, in practice. So how often can I not tell? Well, in fact, you see, intuitively, this has to depend somehow on how distinguishable these two states are, right? Because if they would be almost orthogonal, intuitively it will be the case that this measurement should almost always work, right? While if the two states are almost parallel, then it's the opposite. Then the measurement should almost never work. And so without a surprise, you can quantify that thing nicely. So in general, you can show that the probability to have an inconclusive outcome here, right? So this depends, so this is 1 minus the norm of the overlap. Okay, so here you see it's the overlap between plus and 0, because these are my two states, but this is true in general, right? If I have a psi 1 and a psi 2, the probability of the measurement being conclusive is just 1 minus the overlap, okay? And so in this case here, this is something like 30%. Yes? Yes. Yes, so when you do a projective measurement, the state after the measurement is just the eigenstate, right? Because you project the input state to that one. When you do such a generalized measurement, you know, the final state, it is a bit more complicated, okay? It is not going to be just a projection on the eigenstates. I mean, that wouldn't make any sense here, right? Because the measurement operators are not projectors, okay? You can nevertheless write a formula for what the post-measurement state is. I don't think I wrote it last time, maybe because, you know, I was getting late. So, but if you look in the notes, there is the explicit formula. So the point is, if you know what the measurement operators are, and you know what the state is, there is an explicit formula for what is the state after the measurement. Okay, but what is important is that in any case, the state after the measurement will be modified. Okay, so that means if your measurement, whatever it is, gives you some information, even if it's very little, okay, then the state after the measurement has to be perturbed. Okay, and this you can check from this formula.
Sorry, in this case, for E3, we only have 3 outcomes, or we have more? If we do a measurement with E3, we only have 3 outcomes?
So yeah, so this example here of a POVM, this is one that has 3 outcomes. But I can also invent ones that have 4 outcomes, or even infinitely many. Okay, I can invent that. That is possible. Yes? Well, I think you were first, but.
Can you just quickly review how we know that if it's outcome 1, the state is definitely plus, and if it's 2, it's definitely 0?
Okay. So you see outcome 1 is associated to a measurement operator that it's proportional to a projector. Okay, and this is a projector on the state 1. Now the state 1, this is orthogonal to 0, right? So if you are in the state 0, your detector will never click in this one outcome, right? This is not possible. So given that you only had 2 possibilities, if it was not the first, it must have been the second. That's the idea. Yeah? Sorry, there was another question. No, you had a question. It was the same one.
Yeah.
Or you figure it out during the meantime. Okay. All right. Okay, so let's continue. So I think this was officially the end of the lecture 1, and now I can go to lecture 2. Now this is about density matrices and entanglement. And so if you want to say it in simple terms, what is going to change now is that instead of looking at 1 qubit, we will look at 2 qubits. Okay? So that seems like a very, very small difference. However, it changes everything. Okay? Because when we have 2, we can start to talk about the properties of one versus the other. Okay? And then we have entanglement and so on. Okay? And then once we have entanglement, we can ask the question, okay, if I have this bipartite system, okay, but if I lock 1/2 away, okay, in my lab I only have access to one particle, and this particle is entangled with another one, but that other one I don't have access to, okay. So then how do I describe the physics of that system? And that brings us to the idea of a mixed quantum state, okay, a state of incomplete knowledge. But okay, let's do that in a pedestrian way. Okay, so let's move to 2 qubits. Okay. So let me write first a state of 2 qubits. I will call it psi again. And so this state, well, you see, I could write a state like this. So first I will write everything in a very pedantic way, just to be sure that you get it right. And then I will start to use shorter notations, okay? So I have 2 qubits, right? So I have one subsystem that I call A. So I'll write a ket A in the state that is inside. And then I have another one which I call B. And I have another ket, okay? And I combine these two by this tensor product here, okay? So I have a vector, tensor, another vector. And so then I can also imagine another state of that bipartite system, namely the 1-1 state. Okay, that is one vector, that's another vector. And now by superposition, you know, any linear combination of this form, this is also, it's also a valid 2-qubit state, right? And this is a pure state. It's again a state of complete knowledge. And you see, of course, I still have my normalization condition, that is this, okay? Yes, so really it's a system of 2 qubits, right? So it means that 0, 1, this is an orthonormal basis for my subsystem A, and 0B, 1B, it's an orthonormal basis for my subsystem B, okay? Yes? Ah, yes. No. I'm just doing an example. But you're right, of course. Then, I mean, now it's the dimension of the whole space is 4, right? It's 2 by 2. And so, indeed, then in a complete basis, there would be 4 states. And you're totally right. In principle, I would need to add the 0, 1 and the 1, 0. But here I'm just doing an example. Okay? Now, what this example shows us is that this is a state that features correlations. Okay, that is going to be an important concept for us. You see, if things are independent from each other, well, then you see, if I consider again this problem where I have a particle and I want to describe its physics, and then there is another particle that sits there. If they're independent, okay, I can just forget about anything else, right? I can only focus on my particle here. If I want to discuss the physics of this thing here, I don't need to consider what's going on Jupiter, right? So that's why you know, independent things, we can just throw them away. Now it gets more interesting when they are correlated, okay? And in fact, here in this state, A and B are correlated in a quantum way because they are, in fact, they are entangled, okay, in this state here. But we will formalize that in a minute. Okay, so let me just illustrate these correlations. So suppose that, so both A and B, so A and B will be Alice and Bob, right? They will be my physicists, and each one has access to one subsystem here. So both A and B measure sigma z. Okay? So then we can ask what is going to be the correlation between the results, right? So what is going to be the expectation value? So the correlation, maybe I write it C, okay? This is going to be given by the expectation value of sigma z tensor sigma z on the state psi, okay? So here I'm using again the Born rule, right, for probabilities. And here you see I have an observable that is the tensor product of two, right? But you know, apart from that, nothing is different to what we did before. Okay, so I can calculate that. Does someone know what the result is? No guess? Okay, so in fact it is just 1, okay? And why is it 1? It's because you see, you will get an norm of alpha squared term from when you have this part here and here, right? Then you will get a norm of beta squared when you have this term here and there, okay? And then you have also cross terms, but these, they cancel, okay? Because 0, 1 form a basis. So you can do it slowly if it's not obvious, but okay. Now, let me just discuss it more in terms of physics. I guess it will be clearer, right? So imagine that Alice here makes the measurement of the sigma z basis first, okay? So what is she going to see? Okay, so if A sees m equal +1, okay, so what does that mean? Well, that means that she's here, right? Now, you see, if she's here, it means that we have collapsed the total state onto that part, right? This part just dropped out. So if the total state is this, right, then when Alice sees the result plus, she knows that Bob will also have the result plus, okay, because the state has been collapsed to this part. So then B will see m equal +1 as well. And, you know, obviously, if Alice saw a minus, okay, so it means that she projected here, so on that part of the total state, well, then Bob, when he measures sigma z, he will also see a minus. Okay, so that is to say that if I look at the product of these two results, the product is always +1, okay? Because it's either a ++ or minus. But the product of these measurement results, this is just C, right? This is the expectation value of sigma z times sigma z. All right? So I see semi-confused people. Okay, so you buy it. Yes? No, you don't buy it. You had a question?
I have a question. So, does that mean a value of 1 indicates maximal correlation?
Yes, indeed.
So this is what you would call maximal?
This, yes. So this, So if I view this as an operator, as an observable, indeed, you can check that the eigenvalues are +1 and -1. Okay? And so the eigenvalue +1 means that the two results are always correlated, while the eigenvalue -1 here would mean that the results are always anti-correlated. Okay? The product is always -1. And if C is equal to 0, then the two things are independent. Okay?
And then a value in between 0 and 1
means some level of correlation. Good. Okay. Now, you see, the fact that there are correlations between A and B in this system means that now, if we are going to discuss our previous problem, right, namely, how does A describe the physics in her lab if she has no access to the other particle? That may now, depend on these correlations somehow, right? So the fact that my total state here is pure and is correlated between A and B, that has an impact on how I locally describe the physics, right? You see, I mean, very naively, one could say, maybe the state of Alice is just going to be an alpha 0 plus a beta 1. Okay? So maybe I just forget about Bob. Okay? But that is wrong, okay? As we will see now. This is not like this that we do the thing. Okay, so now the problem. So our problem is to find out what are the statistics, so the measurement statistics on A if we forget about B. Okay? So now what does that mean? Okay, so we are going to say that A measures some observable, okay? And this observable I will call MA. Now, you see MA might be sigma Z, for instance, or something like this. Now, you see, if I want to calculate things, then already I have a problem, right? Because that thing is not of the right dimension to act on this, okay? So, in fact, the correct way to say it is that this is MA on A and the identity on B. Okay, I do nothing on B. Anyway, I don't have access to it. Okay, so then the measurement statistics is going to be the following thing. So this is going to be my observable MA tensor identity B sandwiched between my state psi, right? So psi is now that thing. Okay, so I can go and slowly rewrite it. That is going to be the following. Again, I think I will put indices everywhere to make it clear. Okay, so that is the result if I compute it. So you see, it's good because it no longer depends on B, right? So that should just be something that is local to A. That's good. Now, this thing has two terms, that thing has two terms, so in principle there should be 4 terms, right? However, there are only 2 in the end. But, of course, this is because 0, 1 on B are orthonormal, okay? So when you take the 0, 0 term here, right? And here in principle you have the 0, 0 and the 1, 1. On A you do something non-trivial, so there we don't know. But on B you do something trivial, you do nothing. So of course the 0, 0 term here can only overlap with the 0, 0 term there, right? And the 1, 1 here will only overlap with the 1, 1 there, right? The cross terms, they go away. All right, so that's why we obtain this. And so now, in fact, there is, so here what we did is we calculated the mean value of our observable MA. Let me just write it like this now, I forget about B. And so this is given by this expression here. And this, I can rewrite it in a very convenient way. So I will write it as the trace of MA times some operator, which I call rho A, okay? And this rho A, so this is with rho A, that is equal to alpha squared 0, 0. Okay, so of course these things, they act on A, but okay, I think now I leave out these subscripts all the time. Okay, so why is that true? Well, okay, this thing is a number, right? So I can always write it as a trace. So the trace is linear, so I can divide these things in sums of traces, right? And if I have the trace of something like that, the trace is circular, right? So that guy, I can put it back here. And so then I have something like this here, right? Yeah, I guess this is simple, but just to explain, okay? And so that object here, that is now a density matrix. Okay, so you see that thing is not a vector, right? That thing, it's a, you see, it's a linear combination of projectors. And in fact, you see, it's more than a linear combination, it's a convex combination, right? Because the coefficients here, they sum to 1. Okay? So what is the interpretation of that state? Well, the interpretation is that with some probability, let me call this P here, I prepare my state in the pure state 0, right? I put the projector here. And with the remaining probability, which is 1 minus P, I prepare it in 1. Okay? But, okay, if I'm not aware of this preparation step, okay, if I don't know in every round if the state was prepared here or there, if I just know the relative probabilities, this is my description of the quantum state. Okay, so it's a state of partial knowledge. Here I don't know everything. Okay, and that's why I no longer write it as a vector. I write it as a density matrix. Okay, so this is, if you want, it's an incoherent because it's just, you know, flipping a coin and mixing things. It's an incoherent mixture between two pure quantum states. Okay, either between 0 and between 1. So that is a density matrix. Okay, and so maybe just another terminology that we will use in some cases is that this is the reduced state of A. Okay, so I had a total state. You see a total state that described the AB system. And if I just want to know what is the state of A, if I want to forget about B, I calculate the reduced state. In fact, you can calculate that state from that one by doing something, by doing a partial trace, okay, by tracing out over the subsystem B, which is effectively what we did here in a sense. And that is how you describe the system. Okay? Yes?
So I'm having trouble distinguishing between quantum correlations like entanglement versus just impartial knowledge of which state it starts out in. So does this density matrix distinguish between those two types of correlations?
Yes, in a sense, yes. But okay, in the following sense, okay? So think again in terms of knowledge, okay? So here is a bipartite state of a system on which I have full knowledge, okay? So I know everything that there is to know about A, B, okay? If you think of such a system classically, if you know everything about AB, then you know everything about A and everything about B. Now, in quantum mechanics, it doesn't need to be the case, okay? So this is a pure state, you know everything about AB. However, when you describe the physics of the state A, this is a mixed state. So here you don't know everything, okay? So in quantum mechanics, it is possible to have full knowledge about the whole, but partial or no knowledge about the individuals. Okay, and that is the signature of entanglement. But okay, we'll come back to that. Okay, maybe the next hour or next week. Okay,
So
but.
can I just ask a question? So if I'm given the reduced density matrix, with that information alone, I don't know whether A is entangled with B or whether A was just prepared in either one.
Of course, yes. Yes. Yeah, because you see the total state. So I have a system of two particles, right? A and B. And here, in this state, they are entangled. Okay, I draw this wiggly line to illustrate that they are correlated. Now, of course, I could also have my particle A just prepared in some state rho A. Okay. Maybe it was entangled with another one. Okay, I don't know, but okay. It could also just be prepared directly as a mixed state. And now here, the state B, well, this could be prepared in any rho B, right? And maybe they are just product, they are completely independent. Okay? In fact, that is very important, right? Because if by just looking at A, there would be a difference between that situation and that one, well, then B could, signal instantaneously to A. Okay, because for instance, B could do a measurement, right? When B does a measurement, that will destroy these correlations. Okay, it will destroy the entanglement. So if B did a measurement, and that would have an impact on anything that Alice can measure here, that would be dramatic, okay? Because in these guys could be, billion miles away, right? And then B does something, and instantaneously A would see, and that cannot be, right? And so that's why this object here again tells you nothing about how it relates to the rest, okay? If you want to check that you have this entanglement, then you need to make measurements on A, measurements on B, and compare them, okay? But yeah, it's a very important point. All right, let's do a break, 15 minutes or 10 minutes, and then we reconvene. Good. All right, so now we answered the question we asked, right? So how do I describe the state of the subsystem A if I forget about B whenever A, B are initially entangled? All right, so now you see, so here we arrive at some object that is in fact very important, okay? And in fact, these density matrices, this is the general form of a quantum state. Okay, I mean, similarly to this distinction between projective measurements and POVMs, right? Projective measurements being just a subclass. Pure states are also just a subclass of density matrices, right? In fact, you see, if I would pick alpha equal 1 and beta equal 0, this thing would just be a projector. So then what does it say? It says with probability 1 you prepare the state 0, So that means it's a pure state, okay? And that's indeed correct. However, whenever you have a sum of different orthogonal terms here, then it's a mixed state, right? State of partial knowledge. And so, so density matrices, these are the general quantum states. Okay, and so they include pure plus non-pure, which we call mixed. Okay, so let's just look at some properties of these operators. So properties. Rho, well, let me write it rho A. No? So rho A is self-adjoint. Okay, this is property 1. Property 2 is that rho A is positive. Okay, this you can understand because of this formula. Okay, so in fact you see this formula here, which is very important. This is the Born rule for general state, right? So this is how you calculate probabilities if your state is not a pure one but a mixed one in general, right? If it's a pure one, you can still use the sandwich thing, right? Because you have a vector. But if it's a mixed one, you have to use this formula, right? The trace formula. You see, obviously, if this is a projector, right? You pass one on the other side, and you have the usual sandwich thing, right? So it's really just the same thing. And so the density matrix must better be positive, right? Because this is the rule for probabilities. So if you find a probability that is negative, that's a problem. Yeah. Okay. So I'm saying something slightly confusing here, right? Because here I talked about an observable. So maybe you see I should make it more specific. So if you have a measurement, okay, so if you have a measurement that I describe again by some collection of operators Ej, right? So if rho A is positive, this means that the probability that I have the outcome J, this is the trace of Ej times rho A. Okay, so this is, strictly speaking, this is the Born rule. Okay, this is for measurement operators, not just for observables. Okay, an observable, here it could be negative, right? But this is because the observable is not a positive operator, because it's the observable, right? It's not a measurement operator. But here, if I really have this measurement described by a collection of positive operators, right? For an observable, these would be the projectors, right? Then each of these expressions is non-negative. And this is due to the positivity of the density matrix. And so the last thing is that rho A is unit trace. So the trace of rho A is 1. And this implies the normalization of probabilities. Okay, because if I sum over J the probability to see output J for my measurement, right? So this is the sum over J of trace Ej rho A. Okay, the trace is linear. I put the sum inside, and the operators, they sum to identity, right? And so that thing, this is just the trace of rho A. And okay, by consistency, this has to be 1, right? So it's similar, you see, it's very similar to the construction for vectors, right? For vectors, I asked that they are normalized. This is to ensure conservation of probability. Here it's the density matrix that has to be normalized for the same reason. Okay? Okay, so now comes one point that is really very important. And so this is the fact that pure and mixed states, they are very different. Okay, they are really fundamentally different objects. And so let's do an example. So let me write first a pure state that we have seen already. This is the plus state. So you see this is it's a coherent superposition, an equal superposition of 0 and 1. Okay, so that is a pure state. And then I can write a density matrix that would be the incoherent mixture between 0 and 1. Okay. So, I mean, at first sight, these two things, they look a bit like each other. You know, I mean, there is the state 0, there is the state 1, and I take a sort of 50-50 mixture between them. Okay. However, they are very different. The difference is that in this case, the relative phase between 0 and 1, it is well defined, right? This is this plus here. So it's a plus and it's not a minus, or it's not anything else, right? It's a plus. This has a meaning, means a 0 phase. Here, this would be an incoherent mixture of 0, 1. Okay, so it's either 0 or 1. There is no phase relation between them. It's just I flip a coin and it's that one or that one. Here, you know, some people say they say 0 and 1 at the same time. Okay, it's a superposition of the two. So these two things are very, very different. So this is a coherent mixture or superposition. Probably mixture is not the good term here. This is a coherent superposition, and this is an incoherent mixture. Okay, so why are they different? So, I mean, if I say they are different, it means that there is at least a measurement whereby I can distinguish them, right? And so, of course, there are many measurements for which I can distinguish them, but so measurement to distinguish. So this measurement, let me pick the mx measurement, okay, the sigma z. So if I calculate the mean value of mx in the state plus, okay, so let me write it like this. So this is plus sigma x plus, this is what? So you remember what are the eigenstates of sigma x? Sorry? No, the eigenstates of sigma x, they are the states plus and minus, right, that I introduced. So if I measure sigma x on plus is an eigenstate, right? So I always get the corresponding eigenvalue, right? So I get plus 1. So the result is always plus 1, right? Which means that the expectation value is always plus 1. However, if I measure mx in the other one, in this row here, okay, so now I need to use the other formula. So this is the trace of mx, sorry, of sigma x rho. Okay. Do you see how to rewrite this matrix in a simpler way? For instance, using the fact that 0 and 1 form a basis. So then what should it be? So if you forget about the 1/2 factor, do you see what is projector on 0 plus projector on 1? The identity, exactly. So that is the identity divided by 2. Exactly. Later on, we are going to call this a fully mixed state or maximally mixed state, right? I mean, intuitively, you see, the identity has no structure, right? In every basis, the identity is the same. So this is this is a state of maximal knowledge. It's a pure state. This is a mixed state, but it's a fully mixed state. So it's the state of minimal knowledge, right? It's a state where there is absolutely no structure. And now, so if I use this identity here, right? So I can replace rho by the identity. So that thing is 1/2 trace of sigma x. And this is 0. Okay, so you see, this is an example, right? So if I do the measurement mx, if I had the state plus here, which is an eigenstate of it, I always get the same result, right? If I have this fully mixed state here, right, which is an incoherent mixture now between 0 and 1 without any phase relation, then the measurement statistics of mx is random, okay? The expectation value is 0. It means that I see 50% of +1, 50% of -1. It's completely random, okay? Yes?
I was a bit lost about the definition of density matrix. So
Uh-huh.
the density matrix is defined based on its properties, or it has a definition and then we consider it as this form?
No, you could say it is defined like this.
And then
Mm-hmm.
from these properties, how did you write the density matrix to be that matrix 0, 0 plus 1/2, 1, 1?
Mm-hmm. Yes, okay. Well, so first of all, you see that this is a valid density matrix, no? Because it is a positive. You see the eigenvalues are 1/2, 1/2, right? And it's normalized. Oh, okay, and it's self-adjoint. So this is a valid density matrix. Then here I just use the completeness relation, right? The fact that 0, 1 form a basis. So the projector on 0 plus the projector on 1, by definition, this closes the space. It's the identity. Okay, so this is just another way to write this. But you see, if I write this as a 2 by 2 matrix, it also has the right properties, right? So it has the 1/2, 1/2 eigenvalues on the diagonal, and it sums to 1. So okay.
For example, you can also write plus, 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 minus, minus, whatever that is valid would be the density matrix, or it depends on the system.
So any matrix that has these three properties represents a valid mixed quantum state. Sorry, a valid general quantum state. Yes. Mm-hmm. Now, in fact, it's a good question. I see where your question comes from. Because, you could say, in a sense, the story with vectors, it was already a bit bizarre. This story is maybe even a bit weirder. Now, in fact, that's not the case, right? So you could see it in two different ways. So if you would start with vectors, right, then by doing this reasoning that we did via this thought experiment with A, B, and so on, then in fact, you directly arrive at this thing, okay? Because that is the only, I mean, you see when we derived that thing here, when we did this, there we just used all the rules that we set out before for the vectors, right? And then we come up with this description here. So that is one element of an answer, that given the rules that we set ourselves for vectors, then when we go to the situation where there are several subsystems, well, we need to introduce this idea here of a more general type of state. In fact, it's even a bit deeper than this, okay? There exists a theorem which is due to Gleason from the 60s. And, you know, this is a time where people, very math-oriented, started to think about the structure of quantum mechanics. And so Gleason derived a theorem where somehow he proves that this thing is the only way to go forward, okay? So he asks, okay, this you can see in the notes, I will not discuss here, otherwise I'll be really too late now with the course. But so the idea of Gleason's theorem is that you demand very minimal properties of your theory, okay? And so, you know, then you ask, okay, so a state should be, you know, an ensemble of information that says what is going to happen when I do different measurements, right? That is a state. It's a description of what is going to be the physics of the system. And so, under minimal assumptions for this description to be consistent, Gleason proves that you need to use a density matrix. Okay, this is the only way you can do it. Or if you want, all other ways are equivalent to it. So it seems a bit weird, but you see, at the end of the day, it's essentially the only solution. But okay, if you're interested, you can read about it in the notes. All right, so so where was I now? Okay, so I did this. Yes, so here I derived the density matrix for a 2-qubit system. So here it's the density matrix of a qubit. But if you are interested in the more general object for higher dimensions, it's all done in the notes, okay? It's basically about doing the same with more indices. So I won't do it here. I don't think it's very illuminating. Yes, so I need to go back. In fact, I can just continue like this. There is one more property of a density matrix, but this is, which is it's not, it follows from the above, right? And this is something very useful that we are going to use. It's the spectral decomposition. So it's, you know, the same idea as we saw for measurements, for observables. So this is the idea that any density matrix rho A takes the following form. It can be diagonalized in some basis, okay? So you can write it as the sum, let me say the sum over J, Pj, J, J, okay? And so where, so Pj are non-negative, they sum to 1, so it's really a probability distribution. Okay, and and J is a orthonormal basis. Okay, so I can always decompose a density matrix. So if you want, any density matrix has a sort of preferred basis. Okay. Of course, I mean, I can write this object in any basis, right? But the point is that there is always a basis that, in a sense, makes it simple. Okay. Okay, so maybe let's again discuss that. So let's say 5. Okay, these are, I call them properties, but these are the defining properties, let's say, okay? So if I have a pure state, this we mentioned already, so if this is given by some vector psi, well then the way to describe it as a density matrix, it is to write it as a projector on that state. Okay? And so because of that, it follows that the eigenvalues of rho A are 1 and 0. Okay, because of the, you see, because of the spectral decomposition, right? I mean, you see, if I take the state, so if I do an example, no? if I take the state 0, and I write everything in the computational basis, then the density matrix, it will just look like this. Okay, so it's diagonal, I see immediately the eigenvalues, right? If I have a state like this, and I also write it in the same basis, then it takes the form 1, 1, 1, 1, 1. So when I see this, you see, then it's less obvious that it's a pure state, no, somehow. However, okay, you see, because depending on which basis I choose to represent my state, okay, it may take a different form, right? You see, these are two pure states, no? So up to a rotation, they are the same. But if I write the density matrix in one basis or the other, they look quite different. Nevertheless, the fact that the state is pure, this is independent of my reference frame, right? It's independent of the basis I choose to describe the problem. And so that's why everything is encoded in the eigenvalues, right, of the density operator or the density matrix, because the eigenvalues, they are independent of the choice of basis, right? Right, okay, so this is for pure states, and so it means that if the eigenvalues are non-zero, then I have a mixed state. Okay, so this introduces the idea that we can try to quantify the purity of a state, right? So is it a state of maximal knowledge or minimal knowledge, or can I actually quantify anything in between? So purity of states. So there are several ways to do it. We will look at two. So the first measure is really the purity. Okay, so this is purity as a property. This is the measure. So this is defined as follows. So you take the trace of rho squared. Okay, so it's really just the matrix multiplication. Now, you see immediately that So if rho is pure, okay, so if the density matrix is like this, okay, then trace rho squared is equal to 1. Okay, because rho squared is itself, okay, is rho. However, you also see that if rho is not pure, okay, if the eigenvalues are not 1 and 0, but I don't know, 0.1 and 0.9, okay, then the trace of rho squared is going to be strictly smaller than 1. Okay, so this thing is a if and only if, okay? Yes, okay, it's the only way. Sorry, it's the other way around, but maybe let me write it. Can write it like this, okay? So you see, this is a trick to introduce a measure that tells us something about how pure our state is. There is more about this in the tutorials of this week, I think. I will say more about some other measure, which is more interesting for us because it has an information theoretic flavor. This is the von Neumann entropy. Okay, and this quantity, it is defined, so we write it S of rho, okay, and this is minus the trace of rho ln rho. So for those of you who know the Shannon entropy, it will remind you something that you take an object times a log of this object, okay, in the Shannon entropy, this is a probability distribution. Here it's a matrix. Okay, so when you see this at first, you say, "Oh God, how I'm going to calculate that thing?" But just remember this. Okay, this makes it very easy. That, I mean, of course, you are free to choose the basis for doing this calculation. So you will obviously just pick the basis where that thing is diagonal, right? Then everything is easy. So that thing is then simply minus the sum over, I called it J, so let me call it J again, Pj ln Pj. Okay? And now if you know the Shannon entropy, then it really looks like a Shannon entropy, right? In fact, that thing would just be the Shannon entropy of the probability distribution Pj, okay? All right. So now we can look at some properties of this one. The first property is that S of rho is equal to 0 if and only if rho is pure. Okay, so entropy is a measure of a disorder, right? Or lack of knowledge. So if you have a state that is pure, there is no lack of knowledge, right? This is a state of full knowledge. So then the entropy is 0. On the other hand, if you have a mixed state, right, it's a state of incomplete knowledge. So then you have some non-zero entropy. So just to check, how many of you know about Shannon entropy? Oh, okay, quite a few. So you see, there is one thing that is it's a curiosity of history, I would say, is that, you know, I guess you would all bet that this idea of the von Neumann entropy came after the Shannon entropy. But in fact, it's the opposite. In fact, you know, von Neumann is this guy who was really a mathematician, right? So he's the one usually to whom it's attributed the first sort of complete version of quantum mechanics. Okay, mainly how we discuss it today. Okay, all the previous approaches, they were, in the end, they all converged to that, right? But everyone had still something slightly wrong, I would say. And so it's only then von Neumann in the 30s who could write down the full theory as we know it today. And it's interesting because you see, von Neumann, in fact, he came close to demonstrating some of the theorems that we are going to see, probably next time, because he thought of quantum system in terms of information, right? He defined this disorder here, this entropy, and so on. So in a sense, he could have invented quantum information theory. Okay, it was a very long time ago, so, and he invented game theory and other things. But it's very interesting that somehow this thing even predates the Shannon entropy. All right. So let me continue on the properties of the von Neumann entropy. The second property is that, so here you see an entropy is non-negative, right? So this is an extremal, the entropy is 0 for pure state. The entropy for finite dimensional system also has a maximum, okay? Because you can only be disordered up to some point, right? Or if you want, the lack of knowledge you have about a state can only be that much. And so it's also interesting to say what is the state with the maximal entropy. So this D here is the dimension of the Hilbert space, okay? So for qubits that would be a 2. And so what do you think would be the state that has the maximal entropy? It's a state that we discussed already before. 1 over D, exactly. So it's the identity state, right? The maximally mixed state. So this is for rho equal identity over D. Okay, so I mean, here I do it for D-dimensional systems. So maybe I write identity index D, right? It's the identity matrix with D lines and columns. Okay, so this is the maximally mixed state. Okay, now it also makes sense. Why do we call it maximally mixed? I mean, yes, there is this intuition that the identity looks the same in every basis. So indeed, that is a state that encodes no information about whatever, in a sense, right? Here, if we think more quantitatively, more formally, we also see that it's the case, right? With our notion of entropy, this is the maximally mixed state. So then there is another property that is concavity. And this is the following thing. This is the fact that if I look at the entropy of a mixture, so if I have a sum over I here of pi rho I, so you see so each rho I here is a density matrix. So if the pi is a probability distribution, that defines a new density matrix, obviously, right? Still has the right properties. Now, you see here, I'm talking about concavity, so I'm asking about the so how does the entropy of the total compare to the entropy of the parts, right? And so this is concave, which means that this is, this is an I here. So this is lower bounded by the average of the entropies. Okay, and this is also a very natural property. If I you see, I have a collection of density matrices rho I, and I prepare them with some probability pi, right? So each one has some entropy. Now, if I mix them all together and I forget about which one is which, I can only increase the entropy, right? Would make no sense that I take things, I mix them, and I reduce the entropy, right? So classically, forgetting information can only increase the entropy. Quantum mechanically, it's not like this, but classically, it's like this. Yes? No, sorry. So rho I, if I want to, if you're perturbed, I can use my notation of before. So this is just an index, okay? So it's a collection of density matrices, all for the same system. So each of these could be a projector, for instance, okay? And then it's like before, but it's just a more general way of writing it, right? And then I have a fourth property, which is, let's call it sub-additivity. It's all a bit formal, but okay. Maybe we need it later on. So if I take a density matrix now of two systems, so rho AB, this is upper bounded by S of rho A plus S of rho B. Okay? And so the last thing is that if A and B are independent, okay, so that means that that you see my state is rho A tensor rho B, okay. So if I take the entropy of that, then this is exactly equal to the sum. Okay. Can you see, is it not too low? So you see, here you already can hint at something we will discuss next time, is the idea that with these von Neumann entropies, we will be able to say something about entanglement and the correlations in the state, right? Because you see, if A and B are independent, so not correlated, then the entropy is additive, okay? But in general, when A, B are correlated in some way, you see the entropy is subadditive, okay? So the entropy of the total thing, it will in general be strictly smaller than the sum of the entropies, okay? I mean, this is sort of intuitive, right? Because you see the knowledge, or think of the entropy as the ignorance I have about the system, right? So the ignorance I have about the AB system, let me try to decompose it on the ignorance I have about A and then about B. Right? So if they are independent, it's clear that my ignorance about this and that object, which have never seen each other, is just the sum of them. Okay, that is good. Now, if A and B are correlated, right? So first I calculate my ignorance about A, okay? Now, given that I know A, maybe now I know something about B, right? So because there are correlations between A, B, the fact that I already know A tells me something about B. And so that's why you see this thing here is in general strictly larger than the entropy of rho AB, okay? Don't worry, if it's a bit vague, you can read it in the notes and we will discuss it in more detail next time. Okay, so I see I'm 5 minutes past. Do you mind if I continue for 5 more minutes because I'm getting super late? Is it okay? Okay. Because that will sort of conclude, yes, that will conclude my discussion on mixed state. And so this last point I want to discuss with you is the Blogosphere. And that will be a sort of complete and very elegant description of density matrices of a qubit, okay, for the simplest system. And so, you see, so the rho, the density matrix for a qubit, this is, or it can be described by a 2 by 2 density matrix, okay, which needs the properties that we saw before. So here is the idea. So we are going to take a basis to represent these objects, right? So this will be a sort of canonical decomposition. And this basis, it consists of, well, first the identity matrix, 2 by 2, and then the 3 Pauli ones. Okay, so one can check that this thing, you know, these matrices, they form a basis of our 2 by 2 density matrices. So it means that any density matrix I can write as follows. Okay, so I need a 1/2 factor here. Okay, maybe let me write it in full. So that's the expression. Okay, and here you see, I mean, I just write decomposition in a basis. So all these coefficients here, they are real numbers, right? Nx, ny, and z. So why do I need a factor 1/2? Well, this is because I need trace 1, right? Identity has trace 2. Okay, so I need a factor 1/2. And the Pauli matrices are traceless. Okay, so you see that I already have the correct properties here. Now I'm going to check what are the properties that these 3 numbers, these 3 parameters, nx, ny, and z, need to have, right? And in fact, well, maybe you can guess it already. These will be vectors on a 3-dimensional sphere, right? And this is the Blogosphere. So the idea is that a representation of any qubit density matrix is given by a point, you know, on or inside the unit sphere in R3. Okay. So this is quite elegant. So you see, the idea is that because rho, so rho, so this means here that rho is positive. Okay. So rho positive implies that the determinant of rho has to be non-zero. And okay, using this formula, we can calculate the determinant. I think this is also maybe in one of the tutorials. I will let you check. I think it is. So that thing is just 1 minus the norm of n squared. Okay? And that thing needs to be non-zero, right? The determinant is the product of the eigenvalues, right? So now you see, for that thing to be non-zero, well, non-negative, sorry, it means that the norm of a thing that we call the vector, right? This has to be no larger than 1. Okay, and therefore we get the sphere in R3. Okay? So some people call it Blogosphere, some people call it Poincaré sphere. Okay, you know, this is the usual story of preferences in the history of science. Okay, so I'm almost done. So now there will be the idea that in fact the length of this vector here, the norm of this vector, which is the Bloch vector, that norm tells us about the purity of the state. Okay, so in particular, if the state is pure, the norm will be 1. Okay, and so all the pure state, they sit on the surface of the sphere, and at the center of the sphere, okay, well, it will be the most mixed state. This will be the identity. And in between, well, there are all the other states of 1 qubit. So how should we do it? Yes, so maybe let's do it for pure states. Okay, so for pure states, instead of using my usual alpha and beta coefficients, I will write it immediately in a convenient form. Okay, so you see that, okay, I use angles, but they satisfy my normalization condition. And so that state, it will be associated to a Bloch vector. And now I put a hat on it because it means that it's normalized, right? And this is the vector sine theta cos phi sine theta sine phi cos theta. Okay? And so now I can try to draw this sphere. So this is always a pretty complicated exercise, but let me try. Okay, so not too bad. And now here I draw the equator, okay? So you see, with a bit of imagination, you see a 3D sphere. And so now, on that sphere, I can represent all those states that we have seen. So usually what we do is that the computational states, okay, so the 0, 1 states, they are the north and south pole of the sphere, right? And then on the equator here, we have the plus, and here we have the minus states. Okay, and you see the plus is the sort of superposition between 0 and 1, so it's intermediate. The minus as well, but then with a well-defined phase, right? On the other hand, if you do an incoherent mixture of 0, 1, you actually go inside the sphere, right? And so if you mix 0, 1 with probability 50-50, you hit the middle here, which is the identity. Okay, this is the maximally mixed state. But you see, if you would also mix the plus and the minus state, okay, then you also arrive at the center, right? It's the same density matrix. And okay, you see there are sort of 2 more states that I need to make the description complete. So these are the states, let me call them plus I, and here it will be minus I. It's the states in the y direction, right, the last one. And so these are states that are like this. Okay, so now I have a pi over 2 phase here, right? And obviously the minus is just that I do this. Okay, and these guys, they are the eigen states of sigma y, right? It's the only one that we didn't see so far. All right, and so if now I would, if I pick an arbitrary point here on the sphere, okay, so that could be some some pure state like this. So that state I have, here I have the angle, this is a theta, okay? And then so this is the sort of azimuth, okay? And then I have the, okay, then I have to look here on the equator where it is. So, yeah, sorry, so here my drawing abilities are really letting me down, but okay, you see what I do, no? I project it back on the equator, and then this defines here some angle with the you know, the reference we put on plus x here, and this is the angle phi, right? And so you see, this is it's a very elegant description, right? Because you see pure states, they're on the surface of the sphere. If you want to mix them, you just go inside. Then you immediately see that any mixture between two orthogonal states is going to be the identity, right? It's very geometrical. And so, so you see, in general, mixed states you can represent by the three components of a vector, right? And equivalently, you can view this as two angles. And so if you just have the two angles and norm one, this is a pure state. But any point inside, you can also describe by shrinking this vector, right? So you can add a norm to your vector. And then you have, again, three parameters, and you describe a general state. Okay, and so maybe the last thing just to finish is that, so given, because this goes back to some discussion we had, so given a known density matrix rho, okay, one can fully characterize it via a procedure that is called quantum tomography. Okay, and this quantum tomography, it is what? So it consists of measuring three things. You measure sigma x, and this will tell you, so the average value of sigma x will be equal to the component x of the Bloch vector. Sigma y will give you ny, and sigma z will give you nz. Okay, so, I mean, for those of you with whom we discussed last time, how does one completely characterize an unknown quantum state? So this is the answer, okay? You do quantum tomography, and with the x measurement, you determine the x component of the vector, similarly with the y and z, and then you have your three components of your vector, and this gives a full description of the density matrix, right? Then you have uniquely identified it. Yes?
But you need repeated measurement.
Sure, you need infinitely many copies. Yes.
Related to the question that someone asked last session.
Yes?
That, by doing measurement, we only can measure the norm of alpha and beta, but
Uh-huh.
here we can
Yeah.
even with common phase.
Exactly. So you see, last time we discussed just this last step. No, we just discussed doing a z measurement. So if you do that, well, then you measure nz. Okay, but yeah, in general, I mean, it's only if nz is equal to 1 or minus 1 that you know already that these two will have to be 0, right? And that means because you see already that you have an eigenstate of your measurement operator. But that is a very specific case, right? And so in general, just knowing nz, let's say nz is 0.5, it still leaves you some uncertainty here, right? And so you have to measure these three things to do it.